Good morning.
Good morning, everybody. Thank you for coming to part 3C of Statistics for Trauma Research. We're just going to talk about analysis of variance and chi-square tests today. We've got things to do, after all. So last time we talked about different types of statistical tests. Basic univariate statistical tests where you have one predictor variable and one outcome variable. And we're still going to continue on along that line. But really, statistical testing, hypothesis testing, just depends on the type of variable, especially the outcome variable that you're looking at, and the number of comparison groups, and your sample size. And we'll get into issues with sample size later. And there are a couple of different ways you can approach this. One is the confidence interval, where you have a range of possible values representing how certain you are about that parameter. When you're calculating a higher confidence level, like if, going from 95 to a 99% confidence level, that confidence interval, again, is going to get wider. So I'm 95% sure I can get within the triple ring of the dartboard, but I'm 99% sure I can get somewhere on the wall when I'm throwing a dart. It's been a while. With a larger sample size, that confidence interval is going to get smaller. So if I know if I can throw 10 darts, I'm more likely to get pretty close to the bullseye. And then if I'm just throwing one dart. And that's just calculated as that point estimate for the parameter plus or minus some margin of error. And the margin of error is that critical value out of the normal distribution times the standard error. Okay. And what we focused on last time was more the t-distribution, doing t-tests. Understanding that, we talked about the normal distribution, but understanding that the shape of the normal distribution changes as your sample size changes. With a smaller sample size, the normal distribution gets shorter and wider. And so that's going to depend on the degrees of freedom. Degrees of freedom calculated as a sample size minus 1 in most cases. And we talked about type 1 error. That's the probability of falsely rejecting the null hypothesis, so finding a significant result when you really shouldn't. And type 2 error, that's a probability of falsely accepting the null hypothesis. That's not finding anything when you really should. That's been the analog to that. Has been the example of somebody sitting on his couch looking for his keys, but too lazy to get up, and saying, okay, not over there, not over there, I guess I don't have any keys. And going back to watching the football game. Here's our normal distribution. Again, remember that just over 95% of observations should be within 2 standard deviations of the mean. So remember 1.96 is our hypothetical 2 standard deviation. There's our hypothetical 95% cutoff there. And we have this matrix for, depending on the type of variable and the number of groups, that's going to determine the actual statistical test that you're going to use. And again, we talked about t-tests and z-tests last time, and we may have touched on the chi-square test as well. And we're going to use these when our data actually follow a normal distribution or follow certain parameters. When they don't, we're going to touch on the non-parametric test. That's going to be next time that we talk. Okay, but before we talked about, we've got 2 groups. How do we determine if their means are the same? That's that 2-sample t-test. But now we can expand that. What if we have more than 2 groups? And so how do we know if one of these things is not like the others, to paraphrase Sesame Street? That's a continuous outcome. We've got k independent samples. So k is just the number of groups. That number is greater than 2, and our null hypothesis in this case is just that all of those means are equal. So mean 1 equal mean 2 equal mean 3, all the way up to however many means you have. Alternative hypothesis is that the means are not all equal. So at least one of these things is different. And here's our test statistic. Again, I know the Greek and all the numbers up there looks a little confusing. What this boils down to, you're going to calculate what's called an F statistic. What this boils down to is looking at the variance of the mean values of all the different groups compared to the variance of all the individual values. And it's just calculating a ratio of those variances. That's why it's called the analysis of variance. In table 4, well, I would have a table 4 here, but that's actually in a particular book. Okay. This example is, okay, so if we look at everybody who tested positive for alcohol out of our patients, that the distribution of blood alcohol concentration happens to follow a normal distribution. And we might be curious, okay, how does the blood alcohol concentration differ depending on the mechanism of injury? Is it any different depending on, so are the drunk motor vehicle occupants more or less drunk than the drunk people who fall down? Or more or less drunk than the drunk people who get beaten up? and we can actually take a look at that. Here's our sample size, the mean blood alcohol concentration, and you can see if you're eyeballing this, that there is some difference there, and the standard deviations there. But if our question is at least one of these things different than the others, it's a little tough to say statistically just eyeballing that data. If we graph it out, here are those mean values and the 95% confidence intervals. We can see that, yeah, some of these things are a little bit higher than the others. And the other thing I want you to notice about this is these are confidence intervals. What you may have noticed in the previous slide, and I'll just go back really quickly, is that we have two categories here that have pretty high numbers. Assaults, we had 287. Falls, there were 210 that tested positive for alcohol. There are a couple that had very small sample sizes. Sports and rec, there were only 9. Other vehicle, there were only 13. Where that comes into play is the confidence interval. So the larger your sample size, the narrower your confidence interval. So falls, you see this very narrow confidence interval around 279.9. Assaults, it's very narrow, around 212.8. Sports and rec, remember there were only 9, so you have a very wide confidence interval, very low level of certainty about where the true value is. Same deal with other vehicle. It's quite a bit wider than these others that you have a large sample size for. But going back to the original question, is there a significant difference somewhere in blood alcohol concentration? And that's where analysis of variance comes in. So our null hypothesis is that the mean BAC is equal across all of these groups. Alternative hypothesis is that the means are not all equal. And we can test this using the F statistic. And we have a decision rule with remember with the t-test, we calculated one particular degree of freedom, and that was the sample size minus 1. With an F statistic like this, where we're comparing two different variances, there are two sources for the degrees of freedom. There's what we call the numerator degrees of freedom, or the between groups degrees of freedom, and the within the groups degrees of freedom. And we have to use that to find what our critical value is to reject. For this, it happens to be 1.89. Okay. Plugging this into a statistical package like SPSS, we'll get an output like this. And this is the classic ANOVA table, where it's divided into sum of squares, degrees of freedom, mean square, and F, and we end up with a p-value. If you recall how we calculated variances, sum of squares is actually the sum of the squared deviations away from the mean value of the sample, and divided by the degrees of freedom gives us a variance. And so the mean square is actually the analog of the variance for between the groups versus within the groups. Then taking the ratio of those mean squares, the ratio of those variances, gives us an F statistic. So it tells us how much these groups compare to each other, looking at their means, compared to how much the individual values vary. And if there's more variances between the groups than within them, then we can say that there's some significant difference between those groups. And in this case, we have a very large F statistic. It's 13, it's over 13, when just over 1.8 would have been significant. And so we can see we have a very highly significant p-value here, less than 0.001. Okay, and we can reject our null hypothesis because we have a very large F statistic, and we do have significant evidence to show that there is a difference. Unfortunately, that's all the analysis of variance itself can tell you, is that yes, there's a difference there somewhere, but it doesn't say where. It just says you have a significant difference somewhere within these groups. So, but you might want to know where. So which one actually has the highest? Or is everybody else pretty well clustered and there's one that's way out of whack? Or are they all different from each other? And to get at that, then we need to go back and do those 2x2 tests, or those individual level t-tests. The problem with that, so if we want to know where the differences are, the problem with that is that the problem of multiple testing bias. And recalling that that we're having as our criteria for rejecting the null hypothesis an alpha of 0.05. So we have a 5% chance of rejecting the null hypothesis just by chance. The more tests that we put together, the higher the likelihood that we're going to reject one of them just by chance alone. And so there are different methods of making our tests more conservative. So we're not just rejecting them by chance alone. And these are their names. I won't get into details of them except to say that Bonferroni, you may hear a lot. Bonferroni is probably the most direct and the most conservative way of adjusting for that multiple testing bias. Essentially, it takes the number of comparisons that you're going to make and divides that alpha, that probability of type 1 error, by that number. And so if you have 4 comparisons, you want to test at alpha of 0.05, you just take 0.05 divided by 4 and makes that alpha that much more strict. And this is what I just said. Okay. I know you can't read that part, but these are the multiple comparisons as produced by SPSS, and it just creates a very large table here for each of these groups. It compares that group with every other group, and so you have a significance of that difference. And a confidence interval. So for example, here we've got motor vehicle compared to falls. Down here we can see that the blood alcohol level for motor vehicle occupant victims is 100 points less than that for falls, and that's statistically significant. Same deal with other. But if we compare motor vehicle occupant with motorcycles, even though motor vehicle occupant is 40 points higher, that's not significant when using that Bonferroni correction. And this is a different method of comparing that. This is called LSD, which is fairly descriptive of it. It's although it's actually the least significant difference, or Tukey's least significant difference, and you can see it's not quite as conservative as Bonferroni, but for those large differences, you still see pretty significant outcomes. So motor vehicle versus falls, we still see some significance there, highly significant difference actually. All right, so that's comparing a continuous outcome across multiple groups. What if we have a discrete outcome? Well, before we talked about comparing proportions, but if you have more than 2 categories, you can't just compare the proportions. What we end up doing is setting up a table and looking at the distribution of the observations and comparing that with what we would expect if the relationship was independent. So in this case, our null hypothesis is that the distribution of outcome is going to be independent of the groups, and the alternative hypothesis is that the distribution of outcome actually is dependent on the groups, or what a lot of people like to say is just that the null hypothesis is false. It's kind of the nuh-uh hypothesis. And our test statistic is just going to be the observed number of observations minus the expected squared divided by expected, and we're going to sum that up across the entire table. This is called the chi-square test of independence. And so if we want to look at, okay, we've got a certain amount of males, a certain amount of females. We want to know if there's a relationship between the sex of our patients and whether they test positive for alcohol. And just glancing at this, it appears that there is. Overall, 31.7% of patients have a positive test. That works out to 35.9% of men and 21.5% of women. How can we say statistically, though? Well, first we want to know what would be the distribution if there was no association. If you recall the independence, if the relationship was independent, then the percent positive would be the same for both of them. So there's 31.7% out of the total number. So we want to know what if it was 31.7% for men and 31.7% for women. And that works out to these numbers here. The actual calculation to find the expected number is taking the product of the marginal totals. So for this cell, for instance, the number of men that we would expect to be positive would be the total number of positive results times the total number of men divided by the grand total. And we're going to compare those expected numbers with the observed numbers that we had. And we're going to calculate a chi-squared statistic. So again, chi-squared is just the sum of the observed minus expected, that squared, divided by expected. So adding those up all across the entire table. And we have a critical value of the chi-squared distribution. And again, there's a degree of freedom here that we've got to calculate, and that has to do with how many categories and how many groups. So that's the number of rows minus 1 times the number of columns minus 1 in the table. So in this case, there were 2 rows and 2 columns. So r minus 1 times c minus 1 is 1. So we only have 1 degree of freedom. And that critical value happens to be 3.84 to reject. So if we get a value higher than that, we will reject the null hypothesis. So computing that all out, again, this is how we would do that. And in this case, we already calculated the expected number. We end up with a chi-square value of 52.4, which is quite a bit higher than what we had calculated as the critical value. This is the SPSS output for that, and we can actually generate a crosstab with the observed and expected numbers. And there are a number of different types of chi-square tests that you can have the computer program return for you. The Pearson chi-square is just a classic chi-square. You can do a continuity correction if you want a little more conservative estimate, and there are a couple others. In any case, all of these are significant for this particular example. And you can have it actually return a risk estimate. This actually is bringing an odds ratio. So we can see the odds ratio is just higher than 2. So we can say that men are the odds of a man testing positive for alcohol is 2 times that for women. So in this case, we can reject the null hypothesis and say that we have significant evidence at alpha of 0.05 to show that alcohol toxicology results are not independent. This is what drives people crazy about statistics, is that we use double negatives a lot. So it is dependent on sex or not independent of patient sex, and that's with a p-value of less than 0.001. So that's highly significantly related with gender. Okay, so going back to our decision matrix for these tests, we've covered chi-square tests for 2 or more groups. With independent groups, 2 samples, we can use that T or Z test. If it's 3 or more groups and we've got a continuous outcome, again, that's going to be analysis of variance. And if they're dependent, we end up using just a what's called a paired t-test, and we went over that before. Next time, we'll talk about this column here. That's the non-parametric tests. Those are the tests where your outcome variable does not follow that normal distribution, or if it's discrete, we have small numbers. So again, analysis of variance, dependent variables, continuous. We can use this with more than 2 groups, and it tells if there is a difference somewhere, but we can't tell where. So we can't tell which groups are different just based on the results of analysis of variance. And so for that, we have to do some kind of post hoc testing. And there are different types of tests that have different, depending on how conservative you want to be. Chi-square is just comparing the distribution of a discrete variable across 2 or more groups compared to what we would expect the distribution to be. All right, so next time, as I was mentioning, we're going to talk about non-parametric statistics, where the data actually don't follow the assumptions for those tests. Often it's because of either a small sample size or because the distribution of the outcome variable is highly skewed and unbalanced. Any questions at this point?